For this video, we are going to discuss about nested quantifiers. So sometimes more than one quantifier may be necessary to capture the meaning of a statement in a predicate na logic. So we say that two quantifiers are nested if one is within the scope of the other. So you can see here visualized two predicates that are nested. So within the scope of this universal quantifier is an existential quantifier that states that there exists y such that x plus y is equal to 0. You can think of it like this. For all x, q of x, for in the q of x is another quantifier that states there exists y p of xy, and the p of xy is a predicate x plus y is equal to 0. So let's have an example. So every real number has its corresponding negative. So how can we express this into its predicate logic na form? So let us assume variables for the real number in its corresponding na negative. So let x be the real number and its negative be y. So we can have a predicate p of xy that denotes x is equal to negative y. So then we can write this statement into for every real number x, there is a corresponding na negative, okay? Or there is a y that is negative. Now, another example, there is a person who loves everybody. So first thing, we have to denote variables for the subjects. And we can see subjects here, person and everybody. So let's say we denote X to be the person and Y denote people or everybody. So we can have a predicate L of XY that denotes X loves Y. So if we replace that with person everybody, then person loves everybody. Okay, so we can express this statement into its predicate logic. There is a person X who loves every person Y. Okay, now what about this statement? For every real number X and for every real number Y, X plus Y is equal to Y plus X. So as you can see, this is the commutative, the law for addition of real numbers, right? So given that the X and Y belong to the real numbers. So what it means is that for all real numbers X and Y, X plus Y is equal to Y plus X. So another example, for all X and for all Y, X is greater than 0 and Y is greater than 0 implies that X times Y is less than 0, given that the X and Y belong to a real set. So what it means is that for every real number X and Y, if X is positive and if Y is negative, then XY is negative. Okay? The product of a positive na real number and a negative na real number is always a negative na real number. But we have to take note of the order of the quantifiers. The order of the nested universal quantifiers in a statement without the other quantifiers can be changed without changing the meaning of the quantifier in a statement. Okay? So the order matters a lot, okay? Especially if quantifiers are of different types. So for example, we have for all x, there exists y such that L of xy is not the same as there exists x for all y, L of xy. So assuming we have the predicate L of xy, denoting x loves y. So this statement for all x, there exists y, L of xy may be expressed as everybody loves somebody. Okay, and then meanwhile, this order on the other hand will then be, mean there is someone, there is a person y that is loved by everyone. So the meaning of those statements is different. Now, The order of nested na quantifiers does not matter if quantifiers are of the same type. So for instance, for all x and y, if x is a parent of y and y is a child of x, so we can have two predicates, parent and child. So the parent can denote x is a parent of y and child can denote y, x is a child of y. So we can express it this way. We have for all x and y, um, if the parent of x is y, then the child of then y is a child of x. Okay, and then for all y and for all x, if x is a parent of y, then y is a child of x. So what will be the proof? Suppose we have a predicate q of xy such that x plus y is equal to 5. So suppose we have this predicate statement, there exists a y for all x such that x plus y is equal to 5. And this will actually evaluate to false. Why is that? This statement, when expressed in English, will be there is a y for all x where the sum of x plus y is equal to 5. So for example, if we pick a y value 2, then for all x, regardless of the value of x, the sum of x plus 2 will always evaluate to 5. So for example, if x is equal to 1, then 1 plus 2, that will also evaluate to 5. If we pick x is equal to 5, then 5 plus 2 will always evaluate to 5. So that means that this statement is not correct and therefore false. Okay. What if we interchange the order of the quantifiers? Now we have for all x, there is a certain value y such that x plus y is equal to 5. And this will actually evaluate to true. So what it means is that for all for all x, there is a certain value y where that will make the sum of x plus y equals 5. So for example, if we pick x equals 2, then what will be the value of y that will make the sum equals 5? Okay, so if x is equal to 2, the y would be 3. If we pick x is equal to 1, then the y would be 4. Okay, so now let's have another example. Suppose we have a predicate q with three variables x, y, z, and it states that xy is equal to z. And suppose we have this predicate statement for all x there and for all y, there exists a z such that xy is equal to z. Then what we do is we pick an x, then we pick a y, and then for all x and for all y that we pick, there will always be a product z. Okay, so meanwhile, let's say we have there exists a z, there exists product z that for all x and for all y. So that means that if suppose the value of z or the product z is equal to 7, then it is true for any value of x and y. Okay, suppose we pick 2 and 5 for x and y. So, and it does not evaluate to 7. So, which means that this statement is false.